Hi and welcome to the AnyLogic Modelers YouTube channel. In this two-part series, we're going to look at how you can optimize your model's performance both in memory consumption and execution speed by making use of a profiler. Now, since an AnyLogic model is just a Java application, we can use the existing tools that most Java developers use called Java profilers to analyze the performance and find memory leaks as well as functions that's taking a considerable amount of CPU processing power. So in this video, we'll be focusing on memory consumption, and in part 2, to which the link is in the description below, you will find the video about optimizing the model's execution performance. So with that, let's dive right into a very simple example model that we're going to be using. So we've got a super basic model here currently. It's got agents that's arriving into a queue, they're being serviced, and then they exit the system. Now, if an agent waits too long inside the queue, it leaves the queue prematurely and it doesn't get serviced. Now, we want to measure the time that an agent that gets serviced spends inside the system. So we've added a time measure start and a time measure end inside our model. Now, this very basic service flow simulation can be representative of a number of real-life processes. For example, callers phoning into a call center, waiting in queue, and if they wait too long, they abandon the call. Or it might be cars waiting for a car wash, and if they wait too long, they get out of the queue, etc. So if you consider yourself an advanced AnyLogic user, you should already be able to anticipate the impact of the structure that we've got here and what it would have on the memory performance. So take a moment, make a prediction, and if you like, put the outcome of your prediction at the end of the video inside the comments. So this is a fairly simple model, so let's run it and see what the performance looks like. Okay, so we'll run it at virtual speed. We can see the model is running, there's no issues, the results seem reasonable. Now, if we open up the developer panel or the console, we can see that we are using almost 500 megabytes of memory. And this is a super simple model, right? So something must be wrong. This is the basis for a much bigger model that we're trying to build. We're going to add in a lot of statistics, functionality, etc. And we're already using 500 megabytes of data with only a small amount of agents inside our model. As we can see here, there's only 4 agents currently in the service pool, and there's the 5 resource agents. So we need to figure out why are we using so much memory. Now, luckily, since AnyLogic is a Java application and Java has been tried and tested for many years, tools exist to help developers with this. So the tool that we're going to be using is called Visual VM. The instructions for installing it on your machine can be found in the blog post on the AnyLogicModeler.com, and the links are in the description below. So once you've got that installed and you're trying to do a memory optimization, what you can do is run the model until the point where you see the memory consumption is at the highest, and then open your Visual VM application, which we're going to do now. Now, once the application is open, you'll see on the left pane, it shows you all the applications that it will see and it can attach to. The two that's coming from AnyLogic is called com.anylogic.database, which is a separate part of the internal AnyLogic database, which you're not going to be looking at, and then the com.anylogic.ms, which is the application. So if you double click on that portion, it will open up this overview window for you. If we hit on the monitor tab, we can see some overall statistics. So currently there's no CPU usage, which makes sense. The model is at the end of its life, so it's not executing anything. And we can have a look at the heap space, and we're seeing that we're consuming almost the entire heap, right? If there's small reductions, it might be due to the garbage collector that removed references and old pieces of memory that's not currently being used. And then there's threads and classes, which we're not going to get into now. So if we get to the sampler page and we click on the memory tab here, you'll see that it shows us a whole bunch of objects and how much heap space they're actually occupying. So what we're going to be doing is we're going to clicking on the heap dump. So we want to take a dump of the current memory consumption and all the objects that live inside of it. And it might take a few seconds, and then it's going to open up this heap dump for us. So we can see there's a summary view, but we want to look at the objects. We want to find out what's the objects that's consuming the most memory currently. Okay, so here if we sort it by size, we see that double is currently at the top, right? But we want to get what is the retained size of what we're getting at. So if we click on it, it's going to calculate the retained sizes. We want to see what is being retained in memory. And this is going to take a few seconds. You can watch the progress here at the bottom. We'll just fast forward to this for the video. Okay, so now that we've calculated the retained size of all the objects, we can use this aggregation here at the top to choose where we want to see instances or objects. So for now, we're just going to click on this objects, on the classes, and make sure that we're looking at the retained sizes. So the first problem that we see here is that linked hash map is by far the biggest. We've got 98 counts of this linked hash map reference, or this linked hash maps, and we can see we've got a linked hash map here that contains 97,000 elements. Okay, so let's have a look and see who is referencing this linked hash map. So if we look at the references here, we can see that time measure start is referencing this linked hash map, right? Now, time measure start is an internal AnyLogic block. It's not something that we created. So we need to figure out why is it keeping this reference. If we dive deeper, it doesn't give us that much more information. So let's have a look at the next element in our list, which is the time measure start. Okay, we can see there's only one instance of it. And why is it so big? You know, we're not sure, but we know that it's keeping this linked hash map inside of it, and the linked hash map is extremely big. We can see the third entry here is a car, and we've got 98, it's the linked hash map entry. There's 98,000 of them. Okay, that's fine. That's going to probably be the same thing. It's part of the linked hash map that we've got here at the top, so that doesn't really help us. And if we look at the car, and this is our first red flag, is there's 97 instances of the object car inside memory, which if we have a look at our model, there's only 175,000 cars created, 4 of them inside the system, and 97,972 that's exited through the timeout, right? Okay, so that's an interesting indication. If we sum the amount of cars that left through the pre-exit on the queue and those that are currently in the queue, it actually gives us the exact same number of cars that's being referenced currently. And this would give us this indication to say, okay, something is wrong. We're keeping reference to too many cars. So let's have a look at car number 1, which was created as the first car in the system and should have been deleted a long time ago because there shouldn't be any reference kept to it. And we try and see who's keeping reference to it. We see that it is linked hash map entry 47. And we're trying to figure out which hash map is referencing this entry. So we get this hash map node, and we want to see this is linked hash map 1146. And if we looked at our linked hash map here at the top, we see that 1146 is the culprit. And we know that the only thing that's keeping reference is this time measure start. So if we go back to our model, we've got a lot of hints now, and what we can see is that the number of cars we're keeping reference to is all those that exit out of this queue, and we know that it's a time measure start that's keeping reference to it. And then we realize that we're not removing the references for the cars that travel through time measure start because we don't have a time measure end in there. So now that we know exactly where the problem is in the model, it's very easy to fix. We can literally just add in another time measure end here, which will then reference that time measure start. And even though we're not interested in this capacity, we should tell the model to stop keeping reference to when this car entered the system. So if we run the model now, we'll see that the memory consumption is extremely low. Here at the very, very end, we see that it's about 20%, which still sounds a bit high. Now, one thing you need to know about Java is that it makes use of a garbage collector to manage the memory. So if we go back to our visual VM, and we now connect to that new model, you'll see the old model is now grayed out, it's not available anymore. And we click on the new model, we go to our sampler, we look at memory. You'll see this little button here called perform GC, so garbage collection. So if we hit on the garbage collector, and we then go back to our model, we'll see that it's now 2%. Okay, so the reason for that is that the garbage collector, which is obviously taking up resources, is only executed when it needs to be, right? So when you've got very little memory available, then it runs the garbage collection more often. So having just 2, or now it's showing 4% in your memory usage for such a small model, these are just the basic things required to execute the model. So there's nothing you can do about it. Thanks so much. If you want to be notified about the next video in this series, we will be looking at your execution speed, analyzing the CPU performance. Please subscribe, hit the bell in order to get notified, or check out some of the other blogs at the AnyLogicModeler.com. Thank you so much for watching. See you next time.